Today I'm very excited to talk about the Antarctic ice sheet and theme 1 of SAEF. The Antarctic ice sheet is currently changing rather dramatically, but we still don't understand exactly why it's changing and what it might do in the future. And what it will do in the future is add to sea level, which will profoundly affect humanity. The ice sheet, of course, exists to the south of us. Many of you have been there. It's affected by atmospheric circulation and ocean circulation, and it's going to be the interplay between these two in conversation with the ice sheet that determines its future. And these things work both ways. So, for example, heat from the mid-latitudes is advected towards Antarctica under the ice shelves and causes the ice sheet to melt. Precipitation onto the continent is the source of the ice in the first place, and those two in normal times we would imagine would sit somewhere near balance, but we're not in normal times. And it's really this three-way communication that's going to determine the future of the ice sheet. I was an author on the IPCC SROC report that was published in 2019, and I find this to be one of the most compelling figures from that report. And you can see it shows what sea level is likely to do into the future. It extends up to 2300 AD, so quite a few centuries ahead. And there are two main curves, a blue curve and a pink curve. The blue curve shows what will happen to sea level if we mitigate climate change. This is following an RCP 2.6 scenario. So it means reducing our CO2 emissions to zero and then taking some out of the atmosphere in the near future. Whereas under RCP 8.5, unmitigated climate change, we can expect a very large sea level rise in the near future. In fact, it's predicted to rise by tens of meters in 500 years, for example, if we continue on. So this is not going to stop either. But the major source of uncertainty, so the kind of size of the band here in each of these scenarios, is the contribution from Antarctica. It's still deeply uncertain. And so in SAEF theme 1, we hope to reduce that uncertainty through various ways that I'll be talking about. Today we have a pretty clear indication of what the ice sheet is doing. Here you can see the surface elevation changes of the ice sheet between 2003 and 2019. In West Antarctica, around the Amundsen Sea sector, there's been a very large reduction in surface elevation. But we also see that in some areas that are more familiar to us, like the Thwaites Glacier or the Denman Glacier to the south of Australia. But you can also see that there are sectors of Antarctica where there has been an increase in accumulation from extra snowfall. On balance, the ice sheet is losing mass, but we still need to understand that these gains in accumulation too. And the future of the ice sheet is going to depend on this sort of balance between mass gain and mass loss that we don't really understand. But the key point here too is that our record of observations from Antarctica are extremely short, and we need to do better than that. Since the 5th assessment report of IPCC, one of the most exciting but then very worrying findings is that a sector of the ice sheet, which I just pointed out around Thwaites Glacier, the Amundsen Sea sector, might be experiencing unstable, catastrophic, and unstoppable ice retreat. This is due to a process called the marine ice sheet instability, where as the ice moves backwards on a retrograde slope, so a slope that's deepening into the interior of Antarctica, that ice loss can become progressive and unstoppable. And this is of real concern. So predicting the future of the Antarctic ice sheet doesn't just need us to understand the climate drivers, so the atmospheric circulation and ocean circulation. It also needs us to understand the ice dynamics, which I'm showing here in this figure. And in SAEF, we're going to do both. Around 40 years ago, John Mercer first pointed out that the West Antarctic ice sheet here is an unstable ice sheet and could have catastrophic ice retreat in the sort of coming centuries. That's because of this great big hole underneath the ice sheet. But what you can see is that over around East Antarctica, there are also vast basins where the land is grounded below sea level, and this can cause vulnerability. And in particular, the Wilkes and Aurora subglacial basins are areas where we could see ice sheet loss in the future, and the total sea level potential, if those areas of ice are lost, is 15 to 20 metres of sea level equivalent, which of course would fundamentally transform our coastlines, right? So it's a major concern. And this is just to point out a study that was published this year showing a giant canyon beneath David Glacier in East Antarctica that's 3.5 kilometres deep. It's full of ice at the moment, but this is one of those places where ice retreat could occur progressively and in an unstoppable way. And in that case, it could just lead to quite meters of sea level rise, even from that basin. So we're still just learning about what the bed looks like under the ice sheet right now. In fact, this is still a land surface on our planet that's less well known than the surface of Mars, because it's covered by an ice sheet that isn't transparent. So there's still a lot of exploration to occur in Antarctica to better understand its behaviour. So with that little bit of background in mind, I just wanted to point out the main questions that we think need to be answered. And this is my subset of big questions. Is the present day ice sheet behaviour unusual within its longer term context? We only have 40 years of satellite observations, and it's not enough to understand the ice sheet behaviour and also the climate behaviour over that period. What are the climate and ice sheet processes that are driving modern change? So climate, that would be the interplay of ocean and atmospheric processes. The ice processes are things like marine ice sheet instability that I just described, the dynamic processes in the ice sheet. And which areas in East Antarctica are vulnerable, and how might they respond in coming decades? And this is all leading to one big question, which is how will Antarctica contribute to sea level rise in coming centuries? So theme one has a few different components to it, and I'm not going to speak to these parts, of course, very much. Caroline is going to follow me today. But one of the reasons I came to Monash actually was that there was this opportunity to work with atmospheric modelers within one group. And now this has been extended to this fantastic SAEF program across the whole country that includes scientists from the Bureau of Meteorology, for example. And by understanding the field observations and satellite observations of modern day precipitation delivery to Antarctica, as well as by using climate models, linking climate models to ice sheet models, we've got this exceptional opportunity to understand how Antarctica gains mass through its accumulation processes. And this is really going to help us understand what it's going to do in the future. Because just let me remind you, it was only a decade or so ago, many people thought Antarctica was going to grow into the 21st century. It isn't, but we still need to understand that part of its behaviour. Like I said, the ice sheet observation record that we have is very short from satellites. It's only about 40 years long, but equally the observational record that we have of climate is extremely short. And by using paleo proxy observations, not just from Antarctica, but from the mid-latitudes and also the tropics, we can better understand the processes that link climate variability to change in Antarctica. And by better reconstructing the history of the ice sheet itself, we can answer this question about whether the current day behaviour is exceptional within this sort of longer term context. So I'm really excited about this, of course, because it's my thing, but there's this opportunity to look at onshore and offshore records in Antarctica to reconstruct the history of the ice sheet and understand its behaviour. And I'm just going to give you one quick example of this from my own work. This is from New Zealand supported research in the Ross Sea region. You can see where that is on this map, and the Drygalski ice tongue is a famous feature. It was discovered by Scott in 1904 by his party. We were there in 2017 and 18 to understand the history of this glacier. And I'll just point out that we're working in collaboration with the Koreans who'd mapped all of the bathymetry offshore that helps us understand where the ice used to flow. So thousands of years ago, it flowed along this dotted line rather than where it does today. And by combining offshore geology and onshore terrestrial cosmogenic isotopes, I'll show you what this does in a second, and ice modelling, we better understand how ice sheets respond to climate change. So this is us flying across David Glacier, about 12 kilometers across, up the side of a mountain where we've collected samples the whole way along, up an elevational transect to the top of this mountain. We're just flying into our camp here by the helicopter, so we're going to stop, but actually we worked a little bit higher up the slope. And this allows us, by doing some fancy geochemistry, to reconstruct the history of this glacier. And each one of these points represents a rock sample that we've dated, and these are error bars on the ages. And they show that, that this glacier is thinned by about 160 meters in the last 7,500 years. But fascinatingly, this didn't occur in some sort of uniform manner. There was a rapid change around 7,500 years ago, followed by a period of relative stability afterwards. And this is the work of Jamie, one of my PhD students. And in other locations along the coast of East Antarctica, in the Ross Sea, we've also seen similar behaviour, and by using ice models, we've been able to show that rapid, sort of almost collapse-like behaviour of the ice was due to this retrograde slope sort of ice retreat process, the marine ice sheet instability. This is the very process that could cause the ice to lose mass rapidly in the near future. So combining the geochronology, the offshore evidence and modelling together, we gain insight into a process that's really just hypothesized for the future, but here we've directly observed it. We've been able to quantify, for example, the rates of change that can occur and the duration of an event like this. So we showed that the ice thinned at a rate of about 1 metre per year, and this extended for multiple centuries after the initiation. That's kind of very important for understanding the future behaviour of the ice sheet. So one of the other things that we will do is develop a coupled climate and ice sheet model for Antarctica, and we'll use this to help understand the kind of geological evidence that I just showed you, but we'll also use this model to project the future behaviour of the ice sheet. And this is with collaborators like Rob DeConto at the University of Massachusetts. And one of the things that I'm really excited about within SAEF
3 minutes, Andrew,
is the way that we have cross-theme sort of projects going on. For example, Jan Strugnell, who works on molecular genetics, will be using her approach to understand whether there were open seaways connecting parts of Antarctica that are now ice covered. And this provides an extra constraint for understanding ice sheet history. I'll just give you an example, but the picture here is actually of a coral reef in Western Australia from the last interglacial about 125,000 years ago. It sits just above modern sea level. And we think this represents a time when the Antarctic ice sheet collapsed, or at least the West Antarctic ice sheet. So here's an ice sheet model for all of Antarctica, and this is Rob DeConto's work, one of our collaborators on SAEF. It's a simulation through geological times. It's just thousands of years ago, 300,000 years ago. You can see the ice gets bigger during glacials, it gets smaller during interglacials. But look what happens soon, around 200,000 years ago, you'll see West Antarctica collapse. This is a modelled, reality. We don't know if it actually happened. And by using the kind of techniques that Jan has developed, we can test models like this and understand their sensitivity and therefore do a better job of predicting the future for the ice sheet. So I'm almost there. I hope we're going to answer some of these big questions. Is the present day ice sheet behaviour unusual within its long-term context? By doing the sort of geology work with Geoscience Australia, and I see Kevin, my colleague from New Zealand's here, is on the SAEF program as well. We're going to understand what the ice sheet's been doing in its longer term context. And we'll also have the climate history from the paleo work that Helen's going to talk about after me. And then what are the ice and climate processes driving modern change? Which areas are vulnerable? This will come from the combination of modelling ice sheets and also modelling climate and the coupling between the two in particular. And how will Antarctica contribute to sea level over coming centuries? What I'm hoping we'll do by carrying out this work is reduce that uncertainty band in the sea level projections that I presented at the start of this talk. Now, I've just been focusing on theme one, but obviously SAEF has 3 themes, and there are implications for this work that cross from theme 1 to theme 3. For example, if in the future we're going to have the large-scale deglaciation of sectors of Antarctica, that will have major ecological implications, and then we'll be dealing with the policy implications for that. I mean, how will the treaty cope with, you know, the loss of West Antarctica or the massive retreat of Totten Glacier, for example? So these are things that together I hope we can grapple with as part of the SAEF program. So that's it from me, and I guess I stop sharing my screen and pass over.